So we will read the book as promised. Let's get to it. Hopefully you will enjoy this book. All right. So let's look at a capsule of history. Invention of calculus, explanation of planetary motion, flowering of calculus, 1700s, 1800s, analytical studies of planetary motion. Then we have Poincaré. By the way, chapter what are we in now? 11 Poincaré. Okay. Geometric approach, nightmares of chaos, then nonlinear oscillators in physics and engineering, invention of radio, radar, laser. Then there is 20s and 60s, Birkhoff, Kolmogorov, Arnold, Moser, and complex behavior in Hamiltonian dynamics. And then there is strange attractor, Lorentz, the next chapter. Okay. And then there is turbulence and chaos in logistic map. We already did this. Feigenbaum, universality, renormalization, connection between chaos and phase transition. Already did that, sort of. Then there is Winfrey, nonlinear oscillations in biology, and fractals, widespread interest in chaos, etc. Okay, so what is this? This is an ordinary differential equation because it involves only ordinary derivatives, and this is a partial differential equation, right? Okay, a very general framework for ordinary differential equation is provided by this system. We will not look at partial differential equations. We will be focusing at ordinary differential equations. So here we have x1 dot equals to some function f1 that gets input from x1, x2, xn, and then xn dot. You may be wondering why we don't have x1 double dot, just like here, right? Because we can always reduce this one to that kind of representation. Okay, how do we do it? Of course, dots are derivative with respect to time. The variables might represent concentration of chemicals in a reactor, population of different species, ecosystem, position and velocities of planetary planets, etc. Functions are determined by the problem. For example, the damped oscillator that we just seen, mx dot plus bx dot plus kx equals 0. This is damped oscillation, right? So you can write x dot to be minus b over m x dot, x double dot, sorry, is this, minus kx over m, right? Just like here. Now what you do is you define x2 to be velocity, which is x dot, and you define x1 to be x, which means that this is x1 dot. So in the end, you don't need second derivatives, right? You just have these two equations. Do you have any questions at this point? Any questions at all? Yes. This is chapter 12, not 11. Perfect. What made you wait? Didn't want to break the flow, I guess. Okay, so in the end, thank you very much. This system is linear. Why do we call it linear? Because on the right-hand side, we only have linear functions of x. Okay? So it is a linear system. And we will see that linear systems have a general solution. And we will deal with them. No problem there. Otherwise, you can have a nonlinear system. So for example, this one is nonlinear. Why? Because you can still write it as x1 dot equals x2 and x2 dot equals to minus g over L sine x1, right? Why it is nonlinear? Yes? Because of the sine term. Sine function is nonlinear, right? It starts linearly, but then it bends. Here it is. This will happen very often, that the next page, whatever I want to write is in the next page. Turns out that pendulum equation can be solved analytically in terms of elliptic functions, but there ought to be an easier way. After all, the motion of the pendulum is simple at low energy. It swings back and forth. There should be some way of extracting this information. Here's a rough idea. Suppose we happen to know a solution to the pendulum for particular initial condition. Let me see where it goes. Okay. So if we construct an abstract space with coordinates x1 and x2, then the solution, solution is chaos, right? Yeah. Solution corresponds to a point moving along a curve in space, right? Just like this. This curve is called the trajectory, and the space is called the phase space for the system. The phase space is completely filled with trajectories since each point can serve as initial condition. Our goal is to run this construction in reverse. Given the system, we want to draw the trajectories and thereby extract information about the solutions. In many cases, geometric reasoning will allow us to draw trajectories without actually solving the system. Okay. Some terminology. The phase space for general system is the space with coordinates x1, x2, x3, xn. Because this space is n-dimensional, we will refer to that equation as n-dimensional system or nth order system. So there are, sometimes you have, let me give an example. Okay, here's what I was going to give you as an example. What is this? How would you call this?
A pendulum with a driving force.
Yeah. Would you call it a second order system or?
A second order non-autonomous system or a third order autonomous system.
Very good. So we are going to just keep everything autonomous. Okay? So either you say that, okay, it's a second order non-autonomous system, meaning that this is the system, it has its own autonomy, but we are driving it from outside. So it's non-autonomous. But if we put the finger in, like including this guy as well, then it's a third or three-dimensional system, okay? And it's autonomous. Now I am inside. As a system, we are autonomous. Does it make sense? But then the degree increases to 3. These degrees will be very important. You will see just in a moment why these degrees matter. So here's the trick. The trick is to write this as an equation. x3 equals to t. So you write time as an equation, which means that x3 dot is 1. There you go. You have a three-dimensional autonomous system. Does it make sense?
Yeah.
Yes? Good. All right. Blah, blah, blah. I want to talk about this one. Number of variables and nonlinearity. So let's say you have just one variable and the system is linear. What do you have? You have growth, decay, or equilibrium. That's all you can get. Okay. What are examples? Radioactive decay, RC circuits, exponential growth. Okay. So basically, it's this kind of systems. If lambda is positive, it grows exponentially. Negative, it decays exponentially. Right? Not interesting. If it's nonlinear, then you have fixed points, bifurcations, overdamped systems, relaxation dynamics, logistical equation for single species, etc. Still a bit boring, but more interesting than the linear system, right? Now, if you go to 2 dimensions, you have, and you are linear, then you have oscillation, harmonic oscillator, you have mass and spring, you have RLC system, 2-body problem. If it becomes nonlinear, you have pendulum, anharmonic oscillators, and very importantly, limit cycles. We'll talk about them a lot. Biological oscillators, neurons, heart cells, predator-prey cycles, nonlinear electronics.
I have a question.
Sure.
Here we gave the 2-body problem as an example of a linear system, but isn't it nonlinear?
I think what they mean by this is linearization around the point. But let me think. Why it should be nonlinear?
Because there's gravitational force between them.
Yeah. 2-body problem, linear. I think it's they are mentioning linearization around that point, I guess. But in any case, if you have more than 3 or equal to 3 variables, then you have civil engineering, structures, electrical engineering. But once you hit nonlinear and once you hit n equals to 3, you have chaos. Okay? You have strange attractors, Lorentz system, we will talk about it, 3-body problem, chemical kinetics, iterated maps, fractals, forced nonlinear oscillators, etc. Very interesting stuff. So the next chapter starts here. Okay? Then how about if you have many variables? Then you have coupled harmonic oscillators, solid state physics. That's how we started actually, right? With, you remember bands, band structures and whatnot. Molecular dynamics, equilibrium statistical mechanics. Then in continuum linear systems, you have wave equations, electromagnetism, quantum mechanics, heat and heat diffusion. As you can see, many things are linear, really, right?
Viscous fluids are absolutely nonlinear.
Maybe that's why it's a bit closer here.
Yeah.
No, what you are thinking about is, I guess, non-Newtonian fluids. Is that what you are thinking about? Because if viscosity is constant, doesn't depend.
Stokes equation, which is nonlinear.
Oh, is it? Yeah.
Turbulent fluids are mentioned there in the nonlinear.
But both viscous linear flow and turbulent flow are governed with same equation, only different Reynolds numbers.
I see.
I guess they are talking about some kind of linearization.
I think so. Maybe some assumptions here, like incompressibility, would it help?
For viscous fluids, no, but if we were talking about inviscid irrotational flow, then it could have been the potential flow, so Poisson equation.
Yeah, that's what it is. Okay. Okay. Then over here, let's remind you, it's n much greater than 1. What do we have? We have coupled nonlinear oscillators, lasers, non-equilibrium statistical mechanics, heart cell synchronization, neural networks, economics, ecosystems. What do we have here? General relativity, quantum field theory, reaction diffusion, fibrillation, epilepsy, and life. Okay?
What is fibrillation?
Fibrillation is, you know, defibrillator?
Yes.
Yes. It's when heart becomes doing this thing, like generating these pulses that are creating arrhythmia. Normally it should like beat. It has, I guess, a limit cycle, but then during the fibrillation, we will mention it very briefly, I guess. But during the fibrillation, you basically need to, it comes from inner dynamics. If the cells get into that state, they can't go out. It's like a state in phase space somewhere. So you just reset the system by defibrillator. For some reason I'm smiling, but all right. So flows on a line. Okay, so 1D flows. What do we expect from 1D flows? These things, right? 1D flows. So if it's 1D, then it's just x dot equals to fx, right? Nothing else. Fx can be, for example, consider this system, okay? Can you solve this equation?
Yes.
Yes, you can. How do you solve it?
Separation of variables.
Yeah. Is this a good method? Are you following this method? And this is the answer. You see, instead of x of t, we found t of x. I mean, is it a solution? Yes, it is. But do you understand it? Not at all, right? So that was the point, right? Now we, for example, suppose x0 is starting at pi over 4. Describe qualitatively features of the solution, okay? In particular, what happens when t goes to infinity? You can't answer that by looking at here, right? But you can answer it if you look at it graphically. Look how nice it is now. Okay, so what do? We plot x versus x dot, and let's remind ourselves x dot equals to sine of x, or in general x dot equals to fx. Whenever fx is greater than 0, move to right, right? X increases. Whenever fx is less than 0, move to left. So you draw this, and you notice that over here, f is positive, so we move to right. Over here, f is negative, so we move to left, right? So you immediately see these points. And they are like open circles and closed circles. When they are open, we call them, so fx equals to 0 are called fixed points. Fixed points, right? And if fx equals to 0 goes away, then it's unstable fixed point. If it's going towards it, it's stable fixed point. Can you have a half stable fixed point? Maybe, we will see. But now let's answer this question. If I start at pi over 4, where do I go? I start at pi.
And back.
It's one-way ticket.
Pi over 4.
You start with pi over 4, you reach here, you are happy forever, aren't you? Actually, you are approaching it asymptotically, because as you get closer and closer, fx decreases. So it's just, do you understand it? What if I start at minus pi over 4? Where do I go? Minus pi, right? What if I start here?
Again minus pi.
Again minus pi. What if I start here? Minus 2 pi. So you understand the system just by drawing it. That's the point. Okay. For the sake of having a code, we can look at this thing. I'm using an ODE solver here. Okay, I'm not even bothering writing a code that solves it properly, but it solves it properly, right? And we can change the initial conditions. So let's run it. Ready? So if I start from here, I go to pi. If I start from the right-hand side of 0, I go to left-hand side, I go to minus pi. Right-hand side, I go to pi. Do you see? Are you happy?
Yeah.
Good. Very good. This is exactly what we see. So fixed points and stability. Basically, what we draw here is the phase portrait. We have drawn the phase portrait, we have drawn fx, we have drawn x versus x dot, and this whole thing actually tells us what's going to happen no matter where you start. If you start here, you go here. If you start here, you go here. This is a general thing. If you start here, you go there. If you start here, you fly off there, etc. So it's a geometric approach. I can skip this one. For example, RC circuits, maybe you were having trouble solving them, but look how easy they are if you look at it graphically. So this is the equation, right? Now you can write q dot. Okay, let me not write it again. It's already written here, right? You can write q dot like this. What does it mean? It means that you start from somewhere here, v0 over r, and you go down to q star. And q star is when f of q is 0, which means that v0 over r minus q over rc is 0, which means that q equals to c times v0. So this tells you that there is only one fixed point and it's stable. That's it. Nothing else can happen. No matter where you start, you will end up having c times v0 charge. You remember this filling, emptying, charging, discharging curves. Even if you start over here, you will go there, right? Very good. Very, very good. So for example, sketch the phase portrait corresponding to x dot equals x minus cosine x. Okay, this is a bit more complicated, I guess. But what the book does is it plots x and it plots cosine x, and you can immediately see that beyond this point, x is always winning, right? So this is the only fixed point, and to the right, f is positive, and to the left, f is negative. So it means that it's an unstable fixed point, so it will always fly off to infinity, right? Population growth. We talked about this in terms of logistic map, right? But that was mapping. This is differential equation. This is not asking what will happen next year, but what will happen tomorrow. Like how many sheep remain tomorrow. right? Okay, so if you plot this, you are going to get something like this. So there are two solutions to this equation. So we are looking for the points where dn over dt is 0. Okay, one solution is n equals to 0, which means that no one lives anymore. The other solution is n equals to k, right? That's when also dn or, but luckily, good news is that this is an unstable fixed point. So even if you have a few rabbits, they will grow and they will eventually go to this k. Tell me. Amna, you have a question?
No, I was just reading the text.
Oh, what are you reading? Which one?
The one about when n naught is 0, then there's nobody around to start reproducing.
Yeah, nobody around reproducing, that makes sense, right? N is 0 for all time. The model does not allow for spontaneous generation. Okay. All right.
I have a question.
Sure.
How good is logistics model?
You can read this part, critique of the logistic model.
Alright.
Before leaving this, we should make a few comments about the biological validity. The algebraic form is not to be taken literally. The model should really be regarded as a metaphor for so, okay? It answered your question.
Alright.
For further reading on population biology, go for these guys. All right. Now let's do linear stability analysis, just like we did with mappings. Do you remember maps? We realized that if f prime was, absolute value of f prime was less than 1, then it was stable. Do you remember? In maps. This is not maps. This is flow. When we have a flow, you can see that we are approaching in a similar fashion. Okay. And this time for the flows, the linearization tells you that if f prime is greater than 0, then it grows exponentially. If it's less than 0, then it decays. We can see it already in these plots. What is the derivative? It's positive, so it's unstable. What is the derivative? It's negative, it's stable. Good? Very good. All right. Blah, blah, blah. Let's talk about what can be said about stability if the fixed point has this, if it's exactly 0, right? Then nothing can be said in general. The stability is best determined on the case-by-case basis using graphical methods, okay? For example, this one is stable because this part is plus, this part is minus, so it attracts. This one is unstable. Do you see why? The right-hand side is plus, the left-hand side is minus. The thing that I mentioned, half stable. This is half stable because this is plus here, so it attracts from left, but it repels from right. Okay? This one is, what should we call it? Super stable or something? I don't know. There's a name for it probably somewhere here. Very, very good. Impossibility of oscillations. Fixed point dominate the dynamics of first order systems. As you can see, we have looked at linear and nonlinear systems, both of them, right? And we have seen that, in fact, in all our examples so far, all trajectories either approach the fixed point or diverge to plus or minus infinity. In fact, those are the only things that can happen in real line, right? Do you agree with this? Very good. So a mechanical analog for this would be an overdamped system, but really super overdamped, like having a mass in a honey. So you know that you can stretch the spring, but it will not go beyond the equilibrium point. It will just come and approach and stop, right? Overdamped oscillation. Actually, in the overdamped case, you basically get rid of this inertia part. That's why it becomes one-dimensional system. Solving equations on a computer, you know how to do it. We discussed this, right? Runge-Kutta methods or these Verlet kind of things, etc. Very good. We have made a progress. We have gone over 30 pages. Congratulations to us. All right. What is this one? This one is bifurcations. So concerning bifurcations, we have these kinds of archetypal equations that describe bifurcations. You usually have one parameter, okay, that is varied, and you will see a bifurcation in a way that, okay, let's look at this particular one. For r less than 0, what do you have?
One stable, one unstable fixed point.
Do you see that? One stable and one unstable. But right at r equals to 0, you have a half stable point, right? Then once r is greater than 0, you have no stable points. So you can imagine that you can imagine something like this. Usually stable points are shown by solid lines, and unstable are shown by dashed lines. Okay? Do you remember bifurcation in Feigenbaum? That's what's happening here. But each one of them has its name. So let's look at their names. There is some terminology here. For example, the saddle node bifurcation is sometimes called a fold bifurcation. What was saddle node bifurcation? Was this one saddle node bifurcation? Ah, yes, because of the title. So this is called saddle node. Why saddle node?
It looks like the saddle of the horse you sit on.
Yeah, exactly. But not in a sense that it's like this. More in a sense like a saddle has this part and this part, right? So saddle is actually attracting in one direction and repelling in the other direction. Do you agree? Like Pringles, imagine a Pringles. It goes like this on one side, goes like that on the other side. This video is brought to you by Pringles. Anyways. Okay. So why this is saddle? Because right at the moment when the bifurcation occurs, it's half stable. It attracts from one side, repels on the other side. Make sense? Very good. So you have all kinds of like blue sky bifurcation. Why it's called blue sky? Because it happens out of the clear blue sky. Okay? Etc. Some laser stuff with bifurcations. Pitchfork bifurcation. We like them, so let's look at them. You see, there is an equation, the archetypal equation for them as well. Remember, the other one was something like this. Yeah? This one is different. This one is just Rx minus x cubed. You may be thinking these are arbitrary stuff. They are not arbitrary. In one system, you have this kind of bifurcation, you find that kind of bifurcation. In another, you find a different kind of bifurcation. This is in particular interesting because we have already seen this one in Ising model. Do you remember? There was a beta approximation. We had this line, then the line bent, then passed, and then it became unstable and two stable points. This also looks very similar to what we see in logistic map. Stable point turns into two stable points while the original point becomes unstable. That's also what's going on here, right? So what was the name for it? Supercritical pitchfork bifurcation. Pitchfork because it's like that. Very good. Why supercritical? Because these ones are stable. Okay, that's why it's called supercritical. If it's, is there a subcritical bifurcation here? No, but I guess subcritical would be when you have, I'm guessing, okay, something like this. That can also happen. Anyways, you understand what a bifurcation is, right? Page 41, chapter 4. No, 5. Very good, very good. Are you with me?
Yeah.
It was pretty easy, right? So we are done with 1D flows. Welcome 2D flows. But we will linger here. I mean, it's not as easy as 1D flows. And we are actually going to linger on linear systems. In particular, we will look at 2D linear flows. Okay. Glitching. Two D linear flows. There's a very nice simplification here. You can just write them like this. Do you agree? Two-dimensional system, x and y has to be linear. You may be thinking that, okay, why not add e and f here? Will it be still linear? No? Yes, right? It would be still linear, but you can always shift x and y in a way that these become 0. Okay? So it's a typical two-dimensional linear system, and we will spend a lot of time here. Can you write it like this? Yeah, we are imagining a vector x, which is composed of x and y, and we are saying that x derivative is some matrix times x. I should really... You remember we did this before, right? Way at the beginning. You don't remember? You do remember, yes. So this is your matrix, and this is your vector. Let's see what we can learn about this. For example, harmonic oscillator. Let's write down harmonic oscillator in that sense. So what do we have here? X double dot equals minus omega squared x, right? Where omega squared is not square root. It's just k over m. Do you have any objection to this? No. Which means that you basically have x1 dot equals to x2. Yes or no?
And x2 dot equals minus omega square x1.
Right? So x1, x2 dot is what? Can you tell me the matrix? 0, 1 minus omega squared 0, right? So you can write down the result. Oh, yeah, there it is. It usually happens. You can write down this result as a matrix and you can figure out what is going on. Another way of doing it is you can just plot the phase portrait. How much time do I have? Here's a phase portrait for harmonic oscillator. What we are doing, we are going to this point, right? This is x1, this is x2, and we are basically writing down the arrow based on what is the derivatives, right? And you can see that it basically draws a circle like this. So if you start, harmonic oscillator is a specific system which has conservation, okay? So paths are composed of these conserved quantities, closed loops. You rarely get that, okay, in real systems. You usually have some dissipative thing that would bring things together, okay? Do we have a code for this? I guess we have a code for this, just for the sake of having a code. Here it is, harmonic oscillator, dx over dt is v, dv over dt is omega squared x, and if you run this, you get a phase plot. Very nice. Where did I start? I started from 1, 0. Let me start from 1, 1. I just get a bigger circle. Okay, let's start from 0.1, 0.1. I got a smaller circle. Just the axes were the same, so you didn't see it. Are you happy? Should we stop here? Yes? What we are going to do next is we are going to figure out what different things can happen when you change A, B, C, D, those matrix elements, and we will understand 2D linear systems first. Then we will understand 2D nonlinear systems by going to the fixed points and linearizing the system around those fixed points. Okay? See you next time.